Eval's not so bad either. It's pretty small. It's small partly because of the restrictions on what kind of expression we can have. So in scheme, there are basically 4 kinds of expressions. And they are self-evaluating, which are things like numbers and Booleans. Right? You type in number sign t, its value is number sign t. You type in 23, its value is 23. Those are self-evaluating, which we have in the calculator, namely numbers. There are variables, which we don't have in the calculator. So that's a complexity left out. There are function calls, which we have. They're limited to 4 functions, but they're there. And there are special forms, which we don't have. And when we look at an actual scheme interpreter, we'll see that a lot of the complexity goes into the special forms in eval. So this eval is just a 3-way con clause. If the expression is a number, then we return x, which is the expression. So the expression is its own value. That's why it's called self-evaluating. If it's a list, then it's a procedure call. That's what a list means, call a procedure. And we're going to call calc apply, which I'll talk about in a second, to actually apply that function to arguments. If it's anything other than a number or a list, it's a bad expression. It's an error. Okay? So every list is a procedure call because there are no special forms. So this is a very, very simple version of eval, but something like this is at the heart of every evaluator, because what's an evaluator's job? It takes the stuff that you type in and figures out what that stuff means. And that's eval's job, figuring out what the notation means. If we were writing an interpreter for a language like Java, eval's job would be way more complicated, because there are a bazillion different notations, and they're not uniform. And what you can put in one context is different from what you can put in another context. And so eval is really, really complicated. In Lisp interpreter, eval is much simpler, partly because one complete expression is one list. Okay, so the form of expressions matches the form of the data that the language knows how to deal with. So language was designed in order to be able to evaluate its own programs very straightforwardly. And this is why Lispians say, at the heart of every programming language, there's a Lisp interpreter trying to get out. Because basically, what you have to do is evaluate expressions that are mostly procedure calls and a few other things. And it's just that there's a lot of syntax in the way of doing that. So here, the syntax doesn't get in the way. All right, so we have a very simple eval. But it's not totally simple, because right in here, there's something that is much more complicated than it might look. It's sort of a recursive call, but it isn't a recursive call exactly, because there's no open parenthesis in front of calc eval. Instead, we're using calc eval, which is this procedure that we're in the middle of, as an argument to map. Map is going to call calc eval typically more than once, right? However many sub-expressions there are, however many arguments there are to your operator, we're going to call calc eval once for each of them. So in this expression down at the bottom, we called calc eval on this whole thing. Calc eval says, OK, first thing I have to do is call calc eval recursively for times 3, 4, and also call calc eval recursively for times 5 plus 6, 7. Now, the call for times 3, 4 has to evaluate 3. That's a trivial job, but it has to be done. We have to recognize that this is self-evaluating, and we have to recognize that 4 is self-evaluating. We have to recognize that 5 is self-evaluating, and then we have to say, oh, look, here's another list. So that means another call to calc eval for a function call, and for that one, we have to evaluate the 6 and the 7. Okay? So that's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 calls to calc eval to compute the value of this expression. Okay? So this call to map here is more than just a simple recursive call. It's a multi-way recursive call. And this is the secret to dealing with deep lists right here. That if you have a data structure that's a list of lists of lists of lists to whatever depth you want, then to deal with it, you have to make a recursive call for each element of the top-level list, and then for each element of sublists, and so on, all the way down. So what's the base case for this kind of multi-way recursion? Well, it's the base case of map, which is what? What's the base case of map? Yeah. Yeah, empty list. Okay, map, some function, empty list. Just returns an empty list. Okay? So that's one base case for this process, is that we've evaluated all the arguments. So map is given, 3 arguments or something, and it did a recursive call for the first one, recursive call for the second one, recursive call for the third one, and oops, I have an empty list, finished. Okay, so that's the base case. The other base case is right up here, where if the expression isn't a list, there's no recursion. It's self-evaluating. Okay, so that's 2 kinds of base cases. The way you can think about it is the map base case, think of as being sort of horizontal. You had this expression, this expression, this expression, and you reached the end. And the number base case is like vertical. You've done a recursion and then a recursion inside that and a recursion inside that, and now we're looking at 3. We don't have to do any more recursive calls. But that doesn't mean when we get to this 3, that doesn't mean that the whole problem is solved. I'm betting that despite our discussion about recursive versus iterative processes, a lot of you have in your head the notion that when you reach a base case, everything is finished. Okay, that's not the case here. When you reach this base case of the 3, we aren't going down any further, but now we have to look at the 3's sibling, the 4, and then we pop up and take care of the times 3, 4, and now we have to look at a 5. And so there's a lot of work still to be done when we reach the 3. Even when we reach an end of list base case, so when we've processed the 3 and we've processed the 4, and now we come to the end of this list, that's a base case for map, but we still have this piece to deal with. Okay, so base case doesn't mean the whole job is over. It just means we're not doing any more recursions down this particular road. Okay? Questions about that? Yeah. How does it know to call calc when it sees the plus sign? Oh, thank you. I messed up. Oops. No. Oops. There. It knows because it's not schema, it's in calc. Thank you. Good call. Hard day. Okay. So what's the second argument to map? It's cdr of exp. And this is, we're getting toward one of the ways, well, the principal way, actually, in which the calculator is different from a real scheme interpreter, which is we're not going to see a recursive call for car of exp. Car of exp has to be one of the four symbols, plus sign, minus sign, asterisk, slash. And we're going to use that to represent the function in the call to apply. In a real scheme interpreter, it could be a symbol that's the name of a procedure, but it also could be a lambda expression or another procedure call that returns a procedure, or all kinds of things to provide the function. So we have to eval the car also, but here we're not going to. We're only evaluating the elements of the cdr, which are the arguments to, in this case, plus. And then we're going to call calc apply with two arguments, namely a symbol, plus, minus, slash, asterisk, slash, right? And a list of actual argument values. Okay, because cdr exp is actual argument expressions. Right, so cdr exp looks like this. But map calc eval cdr exp, the result of that is the list 12 and whatever 5 times 13 is. 65? 75? Something like that. No, 65. So the list of two numbers, which are the actual argument values. So this structure, in which we recursively evaluate the arguments before we call apply, is the implementation of applicative order. Got it? Applicative order means first you evaluate the argument expressions and then you call the function. And that's what we're doing here. If we took out the call to map and just called calc apply with car exp and cdr exp, we'd be doing normal order evaluation, where we give the actual argument expressions to the function. Okay? So this is I'm sort of obsessing on a small point, but there's a meta point that I'm making, which is that by reading the code of an interpreter, you can really see the answers to the questions of, what is the language that this interpreter interprets. And here what we're seeing is that the language is applicative order because of this way the call to calc apply is done.